Welcome to Brain Attic. Today we'll continue with the CMOS logic gates lecture. I promised to tell you about the trip point, the derivation of trip point, a little more about the voltage transfer characteristics of the CMOS inverter. Plus I'll give you some hints about past transistor logic, why NMOS and PMOS, NMOS passes a strong 0 and PMOS passes a strong 1. I mentioned this in the previous video. I thought that a brief explanation would be good. So let's begin. Now, so today I'll discuss CMOS operation regions very briefly to you. Why CMOS passes a strong 0, PMOS passes a strong 1 and NMOS passes a strong 0. Voltage transfer characteristics of CMOS inverter in great detail. Also the trip point calculation. So let's begin. First, a very quick review of the region of operations. Before starting this, I expect that you know these things in greater detail, but still for the benefit of this short video, I'll tell you the regions of operations. For NMOS, if you want to keep the device in the off state, then your VGS should be less than VT. To have it in the linear state, a primary condition is that your VGS should be greater than equal to VT, but also your VDS should be less than VGS minus VT. For saturation region, again your VGS should be greater than equal to VT. Now this greater than equal to VT means that your device is on. Once it is on, then you decide whether you want it in linear or in saturation region, or whether the device is in linear or in saturation. So you have to understand these by these equations. For linear, VDS less than VGS minus VT. For saturation, VDS greater than equal to VGS minus VT. So these are the current equations. For cutoff, obviously 0. For linear, half mu n COX W n by L VDS VGS minus VTN minus VDS by 2. For saturation, half mu n COX W n by L VGS minus VT whole square. Okay, moving ahead, for the PMOS regions of operations, we know that for PMOS, my source is connected to VDD and my VT is usually negative. For better clarity, I'm trying to keep the equation same by applying a mod VT, a modular sign over VT. So how does it come? VSG less than equal to VT, mod VT, we are in the off region. Now to keep the PMOS on, we need to have VSG greater than equal to mod VT. So to have the device in linear region, VSD should be less than VSG minus mod VT. VSD should be greater than equal to VSG minus mod VT to have the PMOS in the saturation region. Going forward, these are the current equations for PMOS. Now, one thing to note is that why isn't a negative sign appearing over here? Because my current is in opposite direction to the electrons, but my current is in the same direction to that of the holes. Okay, so even though I'm writing a drain current over here, a minus sign would not appear because I'm dealing with holes when I'm talking about PMOS, and when I'm talking about NMOS, I'm dealing with electrons. So hope you understand, and that's why we keep VDS and VGS as same. Where for better clarity, I'm writing VTP. Okay, that means you apply the negative VT over here and no need of modulus to be applied over here. So once again, we have VDS and VGS. Why so? Even though I'm having a drain current, because the current is in the direction of the transmission of holes or the flow of holes. So these are my current equations. This is for the linear region, almost same with the NMOS, except for a fact that I'm using mod VTP. So my VT might be minus VT. Okay, negative of VT. Same as that for the saturation region as well. Okay, now going forward, now we'll discuss why NMOS passes a strong 0 and a weak 1. Okay, so consider a case where I have a fully charged capacitor connected to an NMOS in this configuration. So for an NMOS, if the potential is high, we make sure that the region is we make note of the region as a drain region, and where the potential is low for an NMOS, we mark it as a source. Okay, so for VGS is equal to VDD. Now this VGS will remain as VDD throughout the process as long as this capacitor is not completely discharged. Now since this capacitor discharges fully, we can conclude that this NMOS is able to pass a strong 0. Shall I repeat? Okay, VDD is logic high. We mark drain when there is high potential for an NMOS. Now this is my NMOS. Hope you remember the symbols. So when the potential is high, on the side where the potential is high, I write it as a drain. On the side where the potential is low, I write it as a source. So my VGS remains as VDD throughout the process, irrespective of the potential on VC. Okay, so my voltage on the capacitor can discharge fully, and thus I can say that NMOS is capable of passing a strong 0. Now, if I connect the capacitor in this configuration, where my drain side, as it is, this is the VDD, and the drain side is connected to VDD, and the source side is connected to a capacitor which is initially completely discharged. Okay, the capacitor is initially completely discharged. So this time my VGS turns out to be VDD minus VC. Now this is a time dependent. For brevity, I haven't mentioned T over here, so this is time dependent. I know for keeping an NMOS on, I need to have VGS greater than VTN. Just now I discussed with you. So continuing with this equation, just a little rearrangement, and we find that my VC can maximum be charged up to VDD minus VTN. Thus we can say that the capacitor is not charged fully. The capacitor is not charged fully, and thus it passes a weak 1. Okay, similar analysis can be done for a PMOS as well. See, this is the symbol of a PMOS. Make sure that the source region, the potential, the side which has higher potential, we mark it as a source region in case of a PMOS. So just for clarity again, I'll mention the higher potential side is the source side for a PMOS. The higher potential side is the source side for a PMOS. The lower potential side is the drain side for a PMOS. Now similar analysis you can perform, and you will find that PMOS can pass a strong 1, but it passes a weak 0. PMOS can pass a strong 1, but it passes a weak 0. Now every time I give a bonus point to you again in this lecture, this is a very important concept for past transistors understanding. This is a very important concept for past transistors understanding. So past transistors are almost similar like this. There's a transistor just connected with a voltage on the gate and a voltage on the drain, and you expect some voltage to appear on the source side. Now this may change according to the configuration or something like that, but this concept remains strong enough for past transistors. Let's move forward. Now you have seen the VDC curve before. Okay, I'll just demarcate the regions for you right now so that you can understand what are the regions. The picture is not quite clear. So before this is my 1. In between these two lines is my region 2. In between these two lines is my region 3. These two lines is my region 3. And in between these two lines is my region 4. Okay, these two lines is my region 4. And beyond that is my region 5. Okay, so this is a VTC. I told you that VTC is V out versus VN. We plot the V out along the y-axis and VN along the x-axis. Okay, so in region 1 we find that the NMOS is off and the PMOS is in linear region. For region 2, NMOS is in saturation, PMOS is in linear region. For region 3, this is the most important region because it has my trip point. Both the NMOS and the PMOS are in saturation. And for region 4, we just make a reciprocal of things. NMOS is in linear, PMOS is in saturation. For region 5, NMOS is in linear and PMOS is off. So I repeat, for region 1, NMOS is off, PMOS is in linear. For region 2, NMOS is in saturation, PMOS is in linear. For region 3, both are in saturation. For region 4, NMOS is in linear, PMOS is in saturation. Just observe this. Here NMOS was saturation, here PMOS is saturation, here PMOS is linear, here NMOS is linear. Okay, now here NMOS is linear, in region 1 PMOS was linear, and PMOS is off and NMOS is off. So just vice versa of the image. Okay, vice versa of the plot I told you. So this is the picture. Observe that. Again I'll tell you, this is my region 1, the area within this is my region 1, this is my region 2, this is my region 2, this is my region 3, okay, and this is my region 4, and beyond this is my region 5, up till here obviously. Now hope you understand the regions. All this calculation can be easily done just by observing the voltages at the gate and the gate, drain and the source side of the respective PMOS and the NMOS in the inverter. Okay, I repeat again, all these regions of operation in an NMOS can be easily observed by noting down the voltages for the CMOS inverter. You can consider a 5 volt. Say for suppose you are giving 5 volt at the input, so obviously my NMOS will be on. NMOS 5 volt at the input, which means that you are somewhere here. Okay, this is the higher side of the VN. So if you are giving 5 volt in the input, so it comes in region 5. If you are giving 5 volt in the input, you are coming in region 5, and your NMOS, obviously your NMOS will be on and it will be in linear region, and since you are giving 5 volt at the gate, your PMOS will be off. True that? Similar analysis can be applied for all these regions. Okay, now for saturation I have shown it. Okay, for saturation we observe trip point by definition is the point where your Vin and Vout are equal. We consider that to be equal to Vm. So see here, I'm writing down the Vin equal to Vm and Vout also equal to Vm. Now I'm just marking the VDS and the VGS values for the respective PMOS and the NMOS that participate in making the CMOS inverter. Observe that for PMOS, the VDS is Vm minus VDD. Okay, so this is my source connected to VDD and my gate is at Vm. So and my drain is also at Vm. So for VDS, Vm minus VDD, Vm minus VDD for PMOS. For NMOS, VDS is Vm. Since my source is at ground, so 0. Okay, so this is Vm. Okay, this is Vm minus VDD, this is Vm. This is Vm minus VDD, this is Vm. Similar analysis can be done. This is Vm minus VDD, gate, this is my gate terminal, and the gate terminal is connected to Vm, so Vm minus VDD. And this is my gate terminal connected to Vm, and the source terminal is grounded, so this is Vm. So hope you understand these things. So both my PMOS and the NMOS are in saturation region for trip point calculation. Now let's go to the main thing. Now during saturation region, the same current flows from the PMOS and the NMOS. Obviously we put a minus sign because the directions are to be reversed, because holes are in the direction of the current, whereas the electrons are opposite to the direction of the current. Holes in the direction of current and the electrons are in the opposite direction of the current. So this minus sign appears because of that, because of the reverse reverse direction of the electrons to that of the current flow, and holes flowing in the same direction to that of the current flow. Now since I told you this is in saturation region, this is my saturation current equation for a PMOS, this is my saturation current equation for an NMOS. A 2 will appear over here, this is whole square. I mentioned the current equations before to you. Now striking out the terminals which are in common, terms which are in common. So half is common, I strike it out. Cox is common, I strike it out. The length of the devices are same, so I strike it out. What I'm left with is minus mu p wp by mu n wn, and these terms over here, whole square, whole square. I told you a whole square is there, so this whole square comes here. There's a whole square, it's just not visible here, so whole square is there. Now I replace this with r, so I take a square root of things, okay, and I replace this with r. So observe that my squares are gone, okay. Now very important point is that when you take a square root of things, you get both a plus and a minus, right? Say for suppose you have a square, and when you take a square root of a square, you say the square root of a is plus a and minus a both, okay? So but for trip point calculation, this minus sign, I'm not going to consider the plus, I'm not going to consider the plus, this minus sign is of importance to me. So moving ahead with the calculation, just observe the calculation very carefully. moving ahead, I replace this VDSP with VM minus VDD. I showed it before to you, okay, a couple of minutes ago. VM minus VDD minus VTP, and this VDSN is just VM. Okay, continuing forward, this is my expression for trip point in case of a long channel device. This is my expression for trip point in case of a long channel device. Okay, simple mathematics, just rearranging things and taking VM out, you get this expression. Note that I have mentioned to you in the first like the prequel of this lecture or this video, I mentioned it to you that for short channel devices and the long channel devices, the expressions are somewhat different. Okay, so what makes them different is that we were considering saturation regions for both PMOS and NMOS in long channel device, but in case of short channel device, we have to consider velocity saturation regions. Velocity saturation regions. I hope you understand what velocity saturation is and how do you find this region and how do you use it in the current equations. Okay, if you just follow the current equations and apply the velocity saturation region expressions to it, then you will be easily able to find the trip point for a short channel device. Now, I gave you a best case scenario in the previous lecture, and I mentioned that VM is equal to VDD by 2. How is this possible? From this expression to moving to this expression. Okay, now this is because we consider R is equal to 1 and VTP is equal to VTN. Now this is quite obvious and easy to understand that how you just consider the threshold point of both PMOS and NMOS to be equal. But how do we get R equal to 1? Just go back and see my R is equal to mu P WP by mu N WN. Okay, so just replacing the expressions, like we know that the mobility of one is twice of the other, and accordingly my width of the devices are twice of the other. Okay, so the electron mobility is higher than that of the hole mobility, and accordingly we have the width of the devices arranged, so the 2 just cancels out and all the expressions cancel out each other and we are left with R is equal to 1. I hope this is clear now to you. So this is my trip point expression for long channel devices. Thank you. If you need some more videos or some more points to be discussed, do mention in the comments below. Don't forget to subscribe my channel and do like this video if you appreciate it. Thank you.